Hello, everyone. I am Mitsunori Uemura of Ritsumeikan University. Let's start the fourth week of the Advanced Topics in Robot Control. This week begins with a continuation of the computed torque method we discussed last week. First, I would like to introduce the computed torque method for multi-joint robots, which have nonlinear motion equations. Next, I prove the stability when we use the computed torque method for a multi-joint robot. Then, we clarify the relationship between the exact linearization concept of nonlinear control theory and the computed torque method. In addition, the task space desired trajectory and inverse kinematics are introduced to control the hand position of the robots when we use the computed torque method. Finally, I would like to introduce adaptive control, which realizes CP control while estimating the physical parameters of the robot online. Let's first introduce how to apply the computed torque method to a multi-joint robot. So let's recall the motion equation of a multi-joint robot. The motion equation of a multi-joint robot can be written like this. Just in case, I would like to explain the dynamics of the robot once again. M is the inertia matrix of the robot. Q is the vector that represents the joint angle of the robot, H is the centrifugal Coriolis term, G is the gravity term, and tau is the vector of the torque exerted by the actuator attached to the joint. The control objective in CP control of the multi-joint robot is to let the joint angle vector of the robot Q follow the desired joint angle vector QD that depends on time. Then, the objective is also to follow the joint angular velocity vector and the joint angular acceleration vector to the target joint angular velocity vector and angular acceleration vector. Just like the basic computed torque method introduced last week, let's calculate the torque tau d required to generate the desired motion. Because the required torque tau d should make the joint angular acceleration vector q2 dot of the robot the desired joint angular acceleration vector qd2 dot. Tau d is calculated by substitutes qd2 dot into q2 dot of the robot dynamics. Let's confirm whether this tau d actually makes the joint angular acceleration vector q2 dot the target joint angular acceleration vector qd2 dot by substituting tau for tau in the equation of motion. At this time, H and G appear on both the left and right sides of the dynamics, and these are cancelled out. The only remaining terms are mq2 dot on the left side and mqd2 dot on the right side. multiplying the inverse matrix of the inertia matrix M from the left of both sides yields Q2 dot equals QD2 dot, which confirms realization of the joint angular acceleration tracking. However, tracking the joint angular acceleration vector alone cannot achieve the control objective regarding the joint angle and angular velocity. Therefore, let's add error feedback terms as in the basic computed torque method. However, in this case, the error feedback terms are multiplied by the inertia matrix M from the left. The reason for this will be explained in the stability analysis. Kp is the feedback gain matrix for the joint angle, and Kv is the feedback gain matrix for the joint angular velocity. These gain matrices are freely set by the control designer within the range of the positive definite matrix. A positive definite matrix is a matrix in which any quadratic form has a value of 0 or greater. Typically, it is a diagonal matrix where each diagonal element has a positive value and 0 otherwise. If you don't know a positive definite matrix, let's review linear algebra. The error feedback term in the curly bracket is almost the same as passivity-based PD control. The effect of these feedback terms is to bring the joint angle vector and joint angular velocity vector closer to the desired ones. Thus, the principle of the computed torque method in a multi-joint robot is exactly the same as the basic computed torque method. In other words, the computed torque method realizes CP control by exerting the required torque calculated from motion equation in the torque of error feedback. Now, let's create a simulation on MATLAB to get a clear understanding of the computed torque method for multi-joint robots. To create this simulation, let's reuse the simulation of passivity-based control for a multi-joint robot. Input the time from the clock block into the controller block of the reused simulation and calculate the time-dependent desired motion. Furthermore, let's calculate the actuator torque by calculating the required torque tau d from the calculated desired angular acceleration vector and the motion equation of the robot, and adding error feedback terms multiplied by the inertia matrix. To check the simulation results, let's display the desired motion and the actual motion in a graph. Creating this simulation is, as always, homework for this week. Let's take time to create a simulation. Next, I would like to introduce stability analysis when we use the computed torque method for a multi-joint robot. In this case, the Lyapunov function v is defined like this. The first term on the right side of this equation represents the magnitude of the joint velocity error, and the second term on the right side represents the magnitude of the joint angle error. The joint angle feedback gain matrix Kp is a positive definite matrix, and V is then clearly always greater than or equal to 0. If this V decreases with time, the control errors also decrease. This means achieving the control objective. So let's calculate the time derivative of the Lyapunov function v. Differentiating v with respect to time gives the equation like this. To derive this equation, as we have explained so far, we use the fact that Kp is a positive definite matrix, which makes it a symmetric matrix, and the transposition of a matrix or a vector product that is a scalar is a reversal of the order by transposing all of the matrices and vectors. For the term q2 dot on the right side of the v dot, we should substitute the motion equation as before. Therefore, let's derive the motion equation when we use the computed torque method. Therefore, by substituting the control law of the computed torque method into tau of the equation of motion, we obtain this equation. Since the tau d on the right side contains the centrifugal Coriolis term h and the gravitational term, these terms cancel out with h and g on the left side. Then, all the terms in this equation are the inertia matrix M multiplied from the left. Therefore, multiplying both sides of this equation by the inverse matrix of the inertial matrix M from the left yields this equation. The joint angular acceleration vector when we use the computed torque method is then obtained, and let's substitute this in the v dot equation. Then, qd2 dot cancel each other out, and v dot becomes this equation. You can see that the first term in the first parenthesis on the right side of this equation cancels the last term in the whole equation. Therefore, only the term related to the second term in the first parenthesis on the right side remains eventually. Therefore, v dot finally becomes this quadratic form. Since Kv is a positive definite matrix, v dot is negative. From the above, we prove that v decreases with time. This means that the joint angle error and joint velocity error decrease monotonically, which means realization of the control objective. In this way, The computed torque method realizes CP control by the torque tau d required to generate the desired motion and the error feedback. The principle is the same as when considering the simplest example. The slight difference is that the error feedback term is multiplied by the inertia matrix. We need this multiplication to derive the final equation in this stability analysis. The physical meaning of this multiplication is not easy to interpret. Nevertheless, we can think a physical image that artificial potential energy and dampers are set in the space where coordinates are converted by the inertia matrix. In order to view the computed torque method from more general framework, the nonlinear control theory, I would like to introduce exact linearization in the nonlinear control theory. Exact linearization is a control method that transforms x equal fxu, which is the representation of the controlled system handled in the nonlinear control theory, into the linear dynamics x equal ax by properly designing the control input u. If we can convert to such a linear dynamics, we can freely design the stability and control performance of the controlled system by using the linear control theory. The computed torque method can be regarded as an application of the exact linearization in the nonlinear control theory to robots. Let's actually see how the computed torque method linearizes the dynamics. In the computed torque method, the actuator torque vector tau that is the input is designed as shown in this equation. In this equation, the terms h and g have the role of eliminating the centrifugal Coriolis term h and the gravitational term g, which are nonlinear elements of the motion equation of robots. This brings the system dynamics closer to linear. Furthermore, in the computed torque method, a new virtual input, tau dash, is set, and the coordinate of the new input is converted using the inertia matrix M. Substituting this into the motion equation of the robot yields the equation for the joint angular acceleration vector equal to tau dash, as described in the stability analysis. This is obviously a linear dynamics with tau dash as input. In the computed torque method, CP control is realized by designing tau dash so as to realize trajectory tracking for this linearized dynamics. From the above, we can see that the computed torque method is exact linearization in the nonlinear control theory. The computed torque method is very useful as a control method for realizing CP control and is used in many robot controls. However, The computed torque method also has disadvantages because it eliminates the robot dynamics as described above. For example, it is not suitable when we have to consider the dynamics of a robot or an object, such as stable grasping of the object by a finger robot. The computed torque method is also not suitable when some structures and physical parameters of the motion equation of robots are unknown because it requires all of them. This means it has limited effectiveness when operating in an uncertain environment. Furthermore, since it is necessary to calculate all the motion equations of the robot, it consumes a lot of computer resources when applied to a robot having many degrees of freedom, such as a humanoid robot. We can be a better engineer or researcher if we understand the above characteristics and use them properly according to the situation. In the explanation of the computed torque method so far, the desired trajectory was designed in the joint space. However, in practical applications, it is often the case that we design the desired trajectory of the robot hand. Therefore, here I would like to introduce a method of converting the desired hand position trajectory xt to the desired joint angle, angular velocity, and angular acceleration. If qd and qd2 can be converted from xd, we can use the computed torque method even when we design the desired trajectory of the hand position. First, let's calculate the joint angle QD that achieves the desired hand position XD by inverse kinematics. To find the inverse kinematics, let's first calculate the forward kinematics that describes the relationship between joint angle and hand position. In order to understand the principle as easily as possible, consider a two-joint robot with as shown in the figure. The hand positions x and y in the task space can be calculated from this equation by using the angles q1 and q2 of each joint of the robot and the link lengths L1 and L2. If you don't understand this equation, review the kinematics of robots. Let's solve these forward kinematics for Q1, Q2. These solved equations are the inverse kinematics of the robot. Let's calculate the concrete equation yourself as an exercise. Once these equations are obtained, the joint angle QD that realizes the desired hand position can be calculated by assigning the target hand position to x and y in these equations. Next, let's find the desired joint velocity vector QD. If the Jacobian matrix J that correlates the hand velocity vector x and the joint angular velocity vector q is used, The desired joint angular velocity vector qd is the inverse matrix of the Jacobian matrix multiplied by the desired hand velocity vector xd by the definition of the Jacobian matrix. The Jacobian matrix J can be obtained by differentiating the equation of forward kinematics with respect to time. Let's perform concrete derivation by yourself as an exercise. The desired joint angular acceleration vector qd2 is obtained by differentiating both sides of the equation of qd with respect to time. Here, the time derivative of the inverse of the Jacobian matrix is newly generated. This is a little complicated, but we can calculate qd2 if the Jacobian matrix is obtained, so let's derive it concretely. Now, let's create a simulation that realizes trajectory tracking control using the desired hand position on MATLAB using the above conversion from the desired hand trajectory to the desired trajectory in the joint space. For this, we can reuse the simulation of the computed torque method created earlier. All we have to do is replace the desired trajectory of the reused simulation with the desired trajectory of the joint space obtained from the desired hand trajectory using the inverse kinematics. The desired hand trajectory should be set so that the hand moves in a circle. Let's display simulation results of the actual hand position and the desired hand position on the same graph, and check whether the robot hand follows the desired hand trajectory. So let's take a moment and create a simulation. At the end of the introduction to the computed torque method, I would like to introduce the applications of the computed torque method. The computed torque method is often used for robots that require high control performance because it is a good method for trajectory tracking and obtaining high control performance. The humanoid robot needs to control its feet to the desired position fast and accurately to avoid falling over. The computed torque method is considered to be used to achieve high control performance of humanoid robots, which have achieved high motion performance such as jumping and running in recent years. In such cases, the structure and physical parameters of the robot are unlikely to change during the control time period. Therefore, if the structure and parameters of the motion equations of the robot are carefully determined beforehand, they can be used in the computed torque method. This concludes the introduction of the computed torque method. The next control method I would like to introduce is adaptive control. Adaptive control estimates the physical parameters of the robot in real time while calculating the torque required to generate the desired motion using the estimated parameters. By estimating these parameters, adaptive control achieves CP control even if these parameters are unknown in advance. Therefore, adaptive control has the advantage that it can be used in situations where the physical parameters are unknown. This means that one of the disadvantages of the computed torque method has been overcome. However, since adaptive control calculates the required torque in the same way as the computed torque method, the disadvantage of high computational cost is the same as that of the computed torque method. It also should be noted that adaptive control requires a structure of motion equation. In other words, when the robot comes into contact with an object that was not determined beforehand, the structure of the motion equation will be unknown, and adaptive control is not suitable in such cases. Now, in order to understand the principle of adaptive control as easily as possible, let's understand adaptive control from the simplest example, the case of a single-joint robot that can ignore gravity, as shown in this figure. The motion equation of this robot would be I bar q2 dot equals tau, as in this equation, where I bar is I plus mlg square, I is the inertia moment of the robot link, m is the mass of the link, lg is the distance from the joint to the center of gravity of the link, q is the joint angle, and tau is the torque exerted by the actuator attached to the joint. Since adaptive control is also used for CP control, the control objective is to make the joint angle Q follow the desired time-dependent desired angle QD, as is the case with the computed torque method. The same is, of course, true for joint angular velocity and angular acceleration. Next, we calculate the torque required to generate the desired motion. However, unlike in the case of the computed torque method, the parameters of the robot are not known beforehand. Therefore, the estimated parameters are used to calculate an estimate of the torque required to generate the desired motion, tau d hat. This hat indicates that it is an estimate. The tau d hat is designed using the estimated value of I bar hat as shown in this equation. If this I bar hat is equal to I bar, then the tau d hat matches the tau d of the computed torque method. Therefore, if the estimation of the parameters can be achieved, this equation allows us to calculate the torque required to generate the desired motion in the same way as the computed torque method. Adaptive control adjusts the estimated parameter I bar hat in real time by the adaptive law expressed in this equation, where gamma is an adaptive gain that is set freely by the designer of the controller. Why we use this equation for the estimation will be discussed later. The actual control law is such an equation in which the terms of error feedback are added to the estimated required torque tau d hat. From the above, we can see that adaptive control is the same as the computed torque method except for the part for estimating the physical parameters. Therefore, CP control can be realized in the same way as the computed torque method if parameter estimation can be realized. Now, let's create a simulation on MATLAB to understand adaptive control through practice. For this simulation, we can reuse the simulation of the computed torque method for a single joint robot. We should replace the parameter I bar with the estimated one I bar hat and update I bar hat in real time by the adaptive law. To update I bar hat from the adaptive law, we need to numerically integrate the adaptive law. To do this on Simulink, let's output I bar hat dot from the controller block, integrate it with an integral block, and then input the output of that integral block into the controller block. So, let's take a moment and create this simulation. Finally, I would like to introduce homework for this week. This week's homework is to create the MATLAB simulation I described this week and submit it as a report. In the report, please include the figure of the simulation model of Simulink, the program source of the robot dynamics block, the program source of the controller block, the simulation result graph, and the explanation of the simulation contents and the simulation result. Please submit the created report through Manabar. That concludes this week's class. Thank you for your hard work.